In this example, we're looking at the classic questions inside a question problem. We're being told that f is a function defined on this open interval right here, zero point 0.4 to 2.7, and it has the derivative given by this equation. And then, in the way that AP Calc questions like to do, they kind of force us to answer three other questions inside this question. They want to know which of the following statements are true. So as we look at this, the first two pieces, 1 and 2, are talking to us about relative maximums and relative minimums. Relative maxes and relative mins are a first derivative test. We need to find first derivative information to be able to read off relative maxes and relative mins. Then part 3 of this wants to know if it has two inflection points on the interval of 0.4 to 2.7. So this is actually second derivative information. So inflection points come from a second derivative data. What we'll do here is we're actually, again, lucky that we're on a calculator allowed question because we're going to just be able to graph that equation they give us, and we'll then read off the data from that graph to decide which of these statements are true or false. So when we're talking about first derivative data, and we're doing a first derivative test, remember that as you do a first derivative test, what you're looking for off of it when you're reading the graph, when you read the graph of a first derivative, you're reading off the pluses and the minuses of above and below. So wherever that graph is up above here, that's where we would have positive derivatives, and that's where our graph is increasing. Wherever we are down below the x-axis, that's where we have negative derivative values, and that's where our graph would be decreasing. And then whenever we hit 0 on here, that's what we would call critical values. That's where our derivative equals 0. Those are the places we want to look for to see if we've got a max or a min going to be occurring. And when you read off of it, let's just remember what a max or a min would look like. So if I have a critical value, let's say I've got a critical value here and a critical value there. If my graph goes from positive, which means it's going up and increasing, and then changes to negative, a negative derivative value, that tells me that's where it would be going down and decreasing. And you can see from that shape there, that's why I like to draw the arrows on something like this, that I've got a max happening at that particular point in time. So that would be a max in that situation. Then if it went from positive or from negative over to positive here, so if it's going increasing coming up out of there, now you can see we have this down up shape that would have been occurring, and so that's when we would have been looking at a min. So the places where our graph changes from positive to negative or negative to positive, those are the places where we could have relative maxes and relative mins. So the first thing we'll do is we'll just go look at that. And to do that, all we have to do is just go ahead and graph this thing. So we just want to graph that equation, that derivative equation. So y equals the sine of x squared. And they don't actually ask us for the specific places that these things happen, so we don't need to find out where it's happening. We just need to know if it's happening or not. So we're going to graph this, and then we're going to look for those places where it crosses that x-axis, because wherever it crosses that x-axis, those are the places, those are our critical values, and those are the places where we potentially could see a max or a min occurring. So we'll start with that. We open up our calculator, go into the y equals, and we're going to graph the sine of x squared. Whenever we're graphing our trig functions, we want to stay in radian mode. And here, because they limit our window, right, this is what's going to be our x window up above. So we only care about what's happening between x equals 0.4 and x equals 2.7. And so we're going to set our x min to equal 0.4 and our x max to 2.7 before we graph it. So I hit window, set that x min to 0.4, set that x max to 2.7, and then we graph it. And so there's our graph. You could squeeze down your y min and max if you wanted this to look better. But what you should notice as you look at this graph is that we have one place where it's crossing right here and another place where it's crossing the x-axis right there. Those are our two critical values. And what I like to do when I'm doing something like this is I like to just read that off onto an actual first derivative number line to kind of, your brain wants to read graphs like normal graphs, and it doesn't want to read the data off as first derivative data. So you don't want to lose track of what you're actually looking at here. So again, I don't care what the numbers are, but I know that I have a critical value happening here, and I have a critical value happening there. So I would mark those on my number line. And the more of these you do, maybe the better you get at not having to go through the number line step. But when you're taking a test and you know you can get it right by doing this, it's worth the 2 seconds. So then I look back at my graph and I say, okay, now there's my critical value. What's happening to the left of my critical value? Well, to the left of my critical value, that's all up in the positive space. That's positive y values. So when we're talking a derivative graph, a positive derivative is going to tell us that our graph is headed up and increasing. Then looking at our graph again after that critical value, so right here, beyond it, just to the right of it, in between our two critical values, the graph is going down into the negative. So that is a negative derivative, and a negative derivative tells us the graph is going down and decreasing. And then we just do it one last time, what's happening after that last critical value, and we can see just after that last critical value that it's going back up into the positive. So it's going positive again and headed up and increasing. And so now from that little sign chart there, that little first derivative test line, we can go ahead and see that what we have going on is we have a max happening at that first critical value. It's going increasing into decreasing. And we have a min happening at that second critical value. It's going decreasing into increasing. So right now we can say for sure it has a relative max on this interval and it has a relative minimum on the interval. And so we've said that those two pieces are true, and now we have to go talk about the third one. So as you go to talk about the third piece, what you're talking about on that third piece again is now second derivative data. So when you go to read off of your derivative graph, second derivative data, you need to read the derivative of this graph, because if I read the derivative off of my first derivative graph, what I get out is second derivative information. And so to read a derivative off of a graph, you read, I just call it my derivative triangle. Wherever the graph would be headed up, that's where you would have a positive derivative. So in this situation, that would be a positive second derivative. Wherever it's headed down and going that direction, that would be a negative derivative value. And so that would be a negative, that would be a second derivative information. And then whenever it's going horizontal, that's when we'd have 0. And in this situation, because we're reading off second derivative data here, these would be our possible inflection points. So what we need to have happen for it to be an inflection point is we need, first and foremost, we need our second derivative to equal 0 or our second derivative to be undefined. Now, that's not going to be a reality in this situation, but it's something to be aware of. And then the second thing we need to have happen is that it needs to change concavity. So it needs to change from concave up to concave down or concave down to concave up, but it has to change concavity there. So we open back up our graph and now we read it just a little bit differently. So what you want to do is you read this graph now as you're reading off where is it headed up. So starting over here on the left, it is headed up until this little horizontal line somewhere in there, we see that it would change direction. That is a possible inflection point. And so as you read that, you'd say, okay, this is going positive, positive, positive. It's increasing. It hits a 0 right here, and then it starts going negative. So we changed from positive derivative, that's again second derivative data. So it's really saying concave up until this point here, and now it's going to go concave down. So what we have on this now, anywhere we see maxes and mins on this, is really where we're looking at inflection points. So I've got one inflection point happening right here. And then as I read the derivative off coming down here, this would all be negative derivative information. So negative second derivative until I hit a 0 somewhere around that point right there. Again, they don't care exactly where, but we know that somewhere in here we'd hit a 0 derivative, which would be another possible inflection point. And it heads up out of that. So it heads into the positive derivative data. So what you can see is we also have a change going from, this would be negative derivative data, which we're reading off second derivative info. So that is concave down up until this point here, which is where our possible inflection point would be. and then it goes positive after that. So that would be concave up. Again, you're reading the derivative data off of here. So what we can see is that it was concave up and concave down in two places. So it changed concavity and had an inflection point. It had a place where it went 0 twice. And so we can say, yep, we definitely have 2 points of inflection on that interval. So when you're reading off of a first derivative graph, wherever you see those maxes and mins occurring, that's where you have inflection points occurring. So this problem, again, made much easier by the fact we didn't have to do any calculations by hand. We just needed to know how to read off the information we were looking at for first derivative and for second derivative. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.